So let's review stoichiometry. Stoichiometry, we're going to do mole to mole, mass to mass, and volume to volume problems in this video. So stoichiometry is a calculation of quantities or numbers using chemical reactions, and they have to be balanced chemical reactions in order for this to work. So we could answer the problem using stoichiometry. If you want to make 1.5 moles of iron oxide using iron and oxygen, how much do we need of the reactants to start? So using stoichiometry, we will be able to answer that question. So we're going to use a mole ratio derived from the coefficients of a balanced equation. So we've got this balanced equation here, and we're going to look at the coefficients out in front. So there's no number out in front of the nitrogen. Remember, chemists are lazy and they don't write 1. So we've got 1 mole of N2 to every 3 moles of H2. And another way to write this would be 1 mole of N2 over 3 moles of hydrogen. We can write it the other way as well, with our 3 moles of hydrogen on top and our 1 mole of nitrogen on the bottom. Again, just using the balanced reaction and the coefficients out in front to make these ratios. So let's write some mole ratios for these problems. So if we're going to compare our lead oxide, we've got 2 from our coefficient out in front compared to our 1 mole of oxygen. We could also compare our 2 moles of our reactant to our 2 moles of our lead oxide on the reactant side, or product side. So that is how we do mole ratios that we're going to end up using in our problems. So to do a mole to mole calculation, first we need to balance our equation if it's not already balanced for us. We're going to determine our mole ratio, our unknown on the top, our known on the bottom. We're going to start the problem with what we're given. So this is our known. So what do we know about the problem? What is the reactant or product that it's telling us about? And we're going to use the correct mole ratio in order to do this. And we're going to use our grid. So this is our known that's given to us in the problem. So this is coming from the problem. And it's going to be in moles. And then our coefficient of our known from the problem, coefficient of what we're trying to figure out, our unknown. And this is just the mole ratio that we looked at in the last slide. So let's look at an example problem. How many moles of ammonia are produced when 0.6 moles of nitrogen reacts with excess hydrogen? This excess hydrogen just tells me that I've got plenty of it, so I don't need to worry about the hydrogen. It's just a distractor in this problem. So let's figure out who our knowns and our unknowns are. So I'm given 0.6 moles of nitrogen, so I know this. What am I trying to figure out? How many moles of ammonia? So he's my unknown. I'm going to go find those in the problem and identify them to make my life easier. So unknown, ammonia, known as my nitrogen. Now I'm going to set up my grid. I'm going to start with my known from the problem. So 0.6 moles of N2. I want my known on the bottom to get them out of here. So my coefficient out in front of my nitrogen is 1. And then I've got 2 moles coming from the coefficient here of my NH3. So 0.6 times 2, we end up with 1.2 moles of NH3. Okay, let's try the next one. How many moles of MgO, so that's what I'm trying to solve. I want to get to moles of MgO, so that's my unknown. That's what I'm solving for. Are produced when 1.2 moles of O2 react with excess magnesium. Again, excess magnesium, it's just telling me that I've got plenty of it, so I don't need to worry about the magnesium. My known is oxygen. So set up your grid again. Start with the known from the problem, 1.2 moles of O2. I've got moles of O2 on the top. I need it on the bottom to get rid of it. Use that coefficient out in front in the balance equation. 1 mole O2 to the 2 moles of MgO, magnesium oxide. So 1.2 times 2, we get 2.4 moles of MgO. Double check, everything cancels. Moles of O2, and I'm left with my moles of MgO, which is what I wanted in my problem. Okay, so those are mole conversions. Now let's look at mass to mass calculations. So this is going to be a couple extra steps, and we're going to have to use the molar mass now. So begin again with our known. What do we know from the problem? What is it giving us? We're going to use the molar mass to get the moles. This is coming from the periodic table. Use the mole ratios. This is coming from our balanced equation. And then we're going to convert back to grams using, again, the molar mass coming from the periodic table. Okay, so this is going to be a 3-step problem. So our grid is going to look like this. We're going to start with our known. And it's going to give us this in grams. Nothing goes in this part. But I don't want the mass of my known, so I've got to get it into moles. So we're going to use the molar mass of our known, and that's going to be in grams. Then we're going to have 1 mole, because our molar mass is grams per moles, and this is still our known. Now we're going to do our mole ratio, so our coefficient from the balance reaction of our known over the coefficient of our unknown. Now I'm in moles of my coefficient of my unknown, but I don't want moles, so now we need to get rid of our moles of our unknown and get to our molar mass. So that's how you do a mass-to-mass grid. Let's do an actual practice problem here. So we want the number of grams of NH3, so that's going to be our unknown. That's what we're solving for. Produced by the reaction with 5.4 grams of H2, our hydrogen. So he is our known. Excess nitrogen, that's extra information, don't need it. So let's go up in our reaction and label, known, unknown. Start with what we know in our grid, 5.4 grams of H2. Now we're going to use the molar mass. So we've got hydrogen. Hydrogen's mass on the periodic table is 1, but we have 2. So we've got 2 grams per mole. So 2 grams of H2 to every 1 mole of our hydrogen. Now I want to switch from my hydrogen to my ammonia, so I'm going to use my coefficients up here in the reaction. So I've got 3 moles coming from right there to every 2 moles of my ammonia. So 2 moles of my ammonia, but I don't want moles, So now we need to get back to grams using our molar mass. So on the periodic table, N is 14, 14 times 1, H is 1, and we have 3 of those. So 14 plus 3, we've got 17 grams per mole, NH3. So we're going to multiply across 5.4 times 2 times 17 gives me 183.6 divided by 2 times 3, 6. So 183.6 divided by 6 gives me 30.6. And let's check our units. So grams of hydrogen cancels, moles of hydrogen cancel, moles of ammonia cancel, and I'm left with grams of NH3. Let's do one more mass-to-mass problem. So we're looking at the same reaction here. N2 plus 3 hydrogen gives us ammonia, and I need 2 ammonia in order for this to be balanced. So we're going to calculate the number of grams of N2, so he's my unknown, produced by 7.4 grams of NH3. He's my known. Set up your grid. Start with your known, 7.4 grams NH3. Molar mass of NH3 is 17 grams, N14 plus the 3 hydrogen over 1 mole of NH3, but I don't want NH3, so let's switch to nitrogen using our coefficients. So 2 moles coming from the coefficient over the 1 mole of N2, but I don't want moles, so I need to switch into grams using the molar mass. So nitrogen is 14, 14 times 2 is 28 grams. Multiply across, so we're going to do 7.4 times 1 times 1 times 28. That gives us 207.2 divided by 17 times 2 times 1, 34. So 207.2 divided by 34. We end up with 6.1 grams of nitrogen. Our last type of problem is our volume problems. So these are done just like mass to mass, but the mole connector is different. So instead of using the molar mass, we're going to use 22.4 liters in our grid. So our grid looks like this. We're going to start with our known, and it's going to be in liters. So we're going to use our conversion, 22.4 liters to every mole. So then we're going to use our coefficients to switch. So coefficient of our known over the coefficient of our unknown. But I don't want moles of my unknown, so we're going to do 1 mole over 22.4 liters. We're going to solve and get our answer, and we're going to end up with liters of our unknown here. So let's try this conversion. So our problem is if 10 liters of sulfur oxide reacts completely, what is the volume of the sulfur trioxide that is produced? So get our grid set up. So this is going to be our known, so label it in the reaction. The SO3 is going to be our unknown. Start with your known, 10 liters of SO2. But I don't want liters, so let's get it into moles using our correct conversion. but I don't want SO2, so let's switch into SO3 using our mole ratio. So we've got 2 moles of SO2 to 2 moles of SO3, looking at our balance equation, but I don't want moles, so let's turn moles of SO3 into liters. So 10 times 1 times 2 times 22.4 divided by 22.4 times 2, we end up with 10 liters of SO3. One last practice. So if we have 25 liters of oxygen, oxygen is going to be our known. Are consumed in this reaction, how much carbon dioxide is formed? So carbon dioxide is going to be our unknown. So we're going to start with 25 liters of oxygen, 22.4 liters of oxygen to every 1 mole, but I don't want oxygen, so let's use our mole ratio. So we've got 5 moles of O2 in our balance reaction to 4 moles of CO2, but I don't want moles, so let's get moles into liters. 22.4 is our conversion factor. So we're going to do 25 times 1 times 4 times 22.4 divided by 22.4 times 5, and we end up with 20 liters of carbon dioxide. So that's our start of stoichiometry. I hope this helped.